do finish up the handout from last time, and then we'll do the quiz here at the end, so you can leave when you're done. Any questions at all before we get started? Things going all right? Yeah. Oh.
Just a reminder, I'll be in Mass Week today.
You'll be in?
2:30.
Great. So if you've got questions for Hope this afternoon, she'll have her first set of office hours today from 2:30 to 4:30, right? So you get up in the math suite, down one floor, end of the hall, go through the door that's right below the sign that says Math and Computational Sciences, and go right to the right. That's where Hope's office hours are for you to go see her for questions. Right. Other questions at all? All right. Well, last time we talked about reading domain and range off of a graph. That was the example that we used. Talked about last time. We're going to do a couple of other things today, talking about how we can look at inequalities and solve inequalities from a graph if you've got a graph of a function, as well as talk about where a function is going up, where it goes down, where it tops out, and where it bottoms out. So that's the plan for today. Where are my quizzes? Oh. They're there. It was in the wrong folder. I had something else in the wrong folder. That was a problem. All right. This is when I got a little worried. All right, so let's look at this example here where it asks us to solve graphically. All right, so we've got two functions that are graphed for us. One is a graph with a solid line, one's a graph with a dashed line. And we'll talk here in a second about how we know which one's which. That's not necessarily important for the first one. The first one's asking us to use the graph to figure out where the two functions are equal to each other. So if I look at the graph, what points do you think you might be looking at to figure out where the functions equal to each other? Where they cross, right? Where they intersect, right? So I see one here, I see one here, and I see one here. Now, once the values that solve the equation, notice the equation is in terms of x, right? So these points have ordered pairs, x and a y. Which value do you think we want if we're trying to solve for x? You think you want the x coordinate or the y coordinate? The x coordinate, right? Good. We want the x coordinate of those because we're trying to solve for x. So if I go across here, the x coordinate of this first point is what? Negative a half. The next one is positive a half, and the next one is 1. So we can just read off those x coordinates from the graph, and our answer to the first part will be x equals negative 0.5, positive 0.5, or you can write them as fractions if you want, and 1. So again, if it's looking graphically and it's asking you to solve the equation, it's just asking you the x coordinate for the points where they actually cross. Okay. That okay? That's not too bad, right? You're just looking to see where they cross and you're picking out the x coordinate. That's not too bad. Okay, so the next ones are asking you basically which one's higher than the other one when we're doing the inequalities, right? And we want to know the x values for where one's above the other. So in this case, I need to know which graph is which. The other one, I didn't really need to know which graph is which because I was looking for where they cross. If I want to know which one's higher, which one has a bigger y value, I need to know which one's which. Okay? So we're going to do this more in depth later in a different section, but we should be able to pick this out by looking at the highest power x term that I see here. So here we've got a 2x cubed. Here we've got a negative 2x cubed, right? This should help us figure out which one's which. Okay? So each of these graphs is, one of them's the left-hand side, one's the right-hand side. Well, let's ignore the coefficient. We have that x cubed. What does your x cubed graph look like? Here's that. It goes from bottom left to upper right, right? It goes like that. That's a little kind of snaking idea, right? Okay. So it went from bottom left to upper right, like this, right, for x cubed. Okay. Now remember what multiplying by a number in the front does? If we multiply by 2, what does that do? It stretches it. It didn't flip the direction, right? So the 2x cubed would just be the same way. It would just be a little bit stretched, right? Still lower left and upper right. What happens if you put a negative sign in front of it? The negative sign makes it, flips it, right? Flips it upside down. So the negative one should go from upper left to lower right, right? Okay, so let's look at your graphs. The one that's the solid line, this solid line one is going from lower left to upper right. The dashed line is going from upper left to lower right. Okay? So looking at the two sides, is this the solid graph or the dashed graph? It's one or the other. This is a solid. Okay. So again, we're looking at the 2x cubed. You told me that should go from lower left to upper right. So which one should it be, the solid or the dashed? That one's the solid, right? So this one's the solid one. And this is the dashed one. And again, we're getting that information just by looking at what's in front, right? This part right here, the coefficient is positive and it's an x cubed, so it's going from lower left to upper right. And that's how I know that's the solid graph. This is a negative, so it means it got flipped upside down, so it's going that way. And that's how I know it's the dashed graph. Doesn't tell me what's going on in the middle, it's just telling me what's going on the ends. Okay. Like I said, we're going to concentrate on this more later, but just to figure out which one it is, I need to figure out which one it is so that I know which one's higher. Okay. All right, so now look at your graph. I want the solid graph to be above the dashed graph. Where am I looking? If I want the solid graph above the dashed graph, where am I looking? Okay, so the y's are going to tell me which one's above, right? So which regions am I looking at? Am I looking over here? Nope. Am I looking here? Yeah, this one's the solid's above the dash here, right? So this one's a good one, right? That one's a good one. How about here? Nope, the dash one's above, right? How about over here? Well, my solid's the one going on forever. Solid one above the dashed one there? Yeah, okay. So this is a good one, this is a good one, this one's not, and this one's not, right? Okay. So what are my x values here? What x values would I have here? Negative 1/2 to 1/2, right? And on this one, what would we have for here? 1 to positive infinity. So if I go back up here, I've got negative 1/2 to 1/2, and I've got 1 to infinity. And it could be either or, so we'll use that union symbol again. Now, why did I use parentheses rather than brackets? What's telling me to use a parenthesis rather than a bracket? And why is it not included? Yeah, so notice that if I look at my inequality sign, what does that say? Does it say it needs to be equal to? No, so I use parentheses rather than the brackets. Erase all these lines that I have over here now, everywhere. Okay, what about the next part? Same functions, but what am I looking for now? Is this one the solid or the dashed? That one's the solid, right? Since it's less than or equal to, do I want the solid above or do I want the solid below? Below, right? I want the solid below. So looking at my graph again, where is my solid graph below my dashed graph? The leftmost side here, right? The solid is definitely below the dashed over here, isn't it? This is going to go on forever. The solid is below the dashed here. Where else is it below the dash? Yeah, do from a half to 1 again, right? So how would I describe this interval over here? Negative infinity up to, yeah, the negative 0.5, right? And from here to here is 0.5 to 1. So this one will be negative infinity to negative a half and a half to 1. Now, in this case, do I want to use parentheses or brackets? Well, on infinity, what do we always use? Parentheses, right? But what about the rest of them? Because it can be equal to, right? That equal sign there says it can be included. That okay? So again, first thing you got to determine is, for these inequalities, what am I looking for? Do I want one graph to be above the other one or vice versa? We're still going off those intersection points though, right? For what we did for the first part, I still went off those intersection points. All right. So again, that's just solving the inequalities from graphs. And you've got some problems in WebAssign that look like that too. All right. So the last little bit that we have here is talking about where a function goes up, where a function goes down, and where it's constant. So just looking at this pieces here, all we mean by, well, constant, I hope is pretty straightforward. Constant, what does a graph of a constant function looks like? Well, constant function, again, remember, is no matter what you plug in, you get the same thing out all the time. So that should look completely flat, right? So notice on this particular graph, this part would be constant because it's flat all the time. And this part would be constant because it's flat all the time. So when we're looking for increasing and decreasing, we always read from left to right and look at what the function is doing as you go from left to right. The reason why we're reading from left to right is because from left to right, the x's go up, right? So as the x's go up, we're trying to figure out what the y's do. So if I look at this part right here, as you go from left to right, do the y's get bigger or do the y's get smaller? They get smaller, right? They're getting smaller and smaller, aren't they? So since they're getting smaller, we refer to that part as being decreasing. I see another part over here where it's also decreasing. That makes sense? It's just falling to the right as you move from left to right, right? It falls down and to the right. Over here and over here, what's going on? On this piece here and this piece here, what's going on? They're increasing. It's getting, the y values are going up, right? So we call that increasing on those. So increasing should look up and to the right. Decreasing should look down and to the right. Okay. Now the problem asks us for the intervals on which it's increasing. When it asks you for the intervals, this is talking about intervals of x values. Okay. All right. So here, you already told me that it's in, for example, it's increasing from this point to that point, right? Okay. What's the x value here? 0, right? The x value is 0, right? Here the x value is 2. So we say it's increasing on the interval from 0 to 2. Again, these are x values. You use the y value to see if it's going up or down, but we don't actually refer to what the y values are. We're just saying it's increasing from x equal to 0 to x equal to 2. Okay? And by the way, doing increasing, decreasing, constant, we always use parentheses for our endpoints. We don't ever have brackets. Okay? Where else did you say it was increasing? Well, let's assume it goes off forever. So 5 to infinity. And then just like what we do for domain, or what we just did for the inequality before, we'll use the union symbol in between. Again, when you're doing increasing and decreasing, it's x values. You do not use the y values. I mean, you use the y values to say if it's going up or down, but it's intervals of x values. Okay? All right, so what about decreasing? Good grief. Why does it keep shifting on me? What about decreasing? Where can you say the function is decreasing? -3 to 0, and where else? 2 to 3, good. So the x value here is -3. The x value here is 0. So it's decreasing from -3 to 0. X's. X value here is 2. X value here is 3. So it's decreasing from 2 to 3. Again, these intervals refer to x's. We always use parentheses. Okay? So far, so good? What about constant? Where is the function constant? And again, we're referring to the x values. Good. Negative infinity to -3. 3 to 5. Good. The function is flat all the way until we get to -3. And then it's flat again from 3 to 5. Is that okay? Right. So let's do the exact same thing for the next one. And then add in an extra little piece. So the next one says, find where it's increasing, decreasing, and constant. If I look at that graph, is it ever constant? No, there's never a whole flat spot all the time, right? Okay? So that part was pretty straightforward. For constant, it's nowhere. Where is for what intervals of x values is the function going up? Okay, definitely negative infinity to -3, because it's going up here, right? And again, x values. I've got the y coordinates labeled, but the y coordinate value doesn't matter, right? We're talking about intervals of x values. Where else is it increasing? -1 to 3. And where else? 5 to infinity. Everybody see where those are coming from? All right? It's going up here. It's going up here. It's going up here. And again, I know I'm emphasizing a lot, but students get it confused. The intervals we're writing down are x values. Okay? The y value doesn't matter. Okay? It's the x values that we're writing down. What about decreasing? -3 to -1 and 3 to 5. Those parts okay? Okay. Notice there's also an extra thing it asks us about. It didn't just ask for increasing, decreasing, constant. It also asks for local maxima and local minima. Basically, what this means is look for a hill, look for a valley. A maximum is the top of a hill. A minimum is the bottom of a valley. Okay? So it asks for the coordinates of the points. So in this case, we're going to write down ordered pairs. Maxima is the plural of maximum, and then the same thing for minimum. Okay? So local maxima, do you see a hill somewhere? Top of -3, -1. And again, these are ordered pairs, so I do want the x, y. It's asking for the coordinates. Okay? Where else do you see the top of a hill? 3 5/2. Good. The reason why we call them local, is this the highest point for the entire function? Is that the highest the function ever gets? No. So it's not the highest point in the world. It's just the highest point in an area. That's the local piece. Okay. Same thing over here, right? This isn't the highest it ever gets, right? But it is the highest point here. How about valleys? Do you see a valley? Bottom of a valley? Good. -1, -5/2 is one of them. Where else? And 5/1. Good. Again, those aren't the lowest points ever, but they are the lowest points in a little area. That's why they're called local versus absolute would be the other word. I know it's a little bit nasty notation, right? These are intervals of x values. These are ordered pairs, but they look the same, don't they? Make sure you've got the interpretation of which one's which by context, right? These are points. These are intervals. And I know that it sucks. It's just the notation that it's been used for years and we're stuck with. Questions on that at all? We okay with increasing, decreasing, max and min? Okay. All right. So let's see if we can do an interpretation problem here. And then we'll do the quiz. So they've got depth of water in a reservoir over a 1-year period. X is measuring the number of days in a year. And since it's a 1-year period, we really are going to cut this off at 0 and at 365. Okay? So since it's a 1-year period, we're not going to go off to infinity or minus infinity. We're going to just go from 0 to 365. Okay? Where do you see this increasing? Good, 0 to 150. Fantastic. Do you see anywhere else where it is? Good, 300 to the 365. Good, I agree. Good. And again, for increasing, decreasing, always use parentheses for your endpoint grouping symbols, if you will.
So would it be incorrect if you did like the 0 to 100 then 150 because of the thing?
It's not really incorrect, except that it continues to go up through 100, so we don't need to do that. But it's not bad. Yep, yeah, you're fine. Where do we see decreasing? 150 to 300. Good. That okay with everybody for that, for increasing and decreasing? Do you see, see if I can shrink it just a little bit so we can actually get the graph on here at the same time. Do you see a local maximum? Do you see the top of a hill? Now in this case, this one's asking for the value of x. So it's not asking for coordinates of a point, it's just asking for the x. What x value do you see a maximum at? Yeah, the 150. Good. So a maximum at x equal to 150. Do you see a minimum? At 300. Good. Now again, the difference in this particular problem than the previous one is it literally is just asking me for the x value, right? It didn't say the amount or the coordinates. It just said find the x value. So we found the x value. That part okay? All right. Then the last one is just a little bit of a review for us. It's asking for the net change in the depth. Remember your net change, just to write this off to the side, we did this the other day. If you want net change from x equal to c to x equal to d, you do the ending y value minus the starting y value, right? That was net change. How far you went. Okay. So in this context, the function name is w. So we want w of 300 minus w of 100, right? From 100 to 300 is the difference of those two things, right? Okay. Go back up to the graph. What is w of 300 equal to? What is the output associated with 300? 25. What's w of 100? 75, right? So we'll do 25 minus 75. These are the y coordinates, right? Remember, functions you plug in an x, you get out a y. So we're looking for the y coordinate. We get negative 50. Why is it negative? Yeah, because it decreased, right? It went down 50, whatever, feet or meters? Feet? Okay, went down 50 feet. Okay. So the net change is negative, tells you it went down. That's what the negative is telling you. Any questions on that one at all? All right, well, quiz time. When you're done, you can go, so you just turn it in to me. There is a front and a back, so make sure you get both of those things.